pondering if we're alone in the universe. This is due to the thousands of messages they've been getting from space from a single huge and mysterious source. What is sending these messages? Can we ever decode these messages? What is anyone out there trying to tell us? In this video, we dive into the details of how scientists have just detected something huge in space that keeps sending us thousands of messages. For many people, fast audio burst means nothing. However, to astronomers, scientists, and avid space lovers, fast radio burst, or FRB, is one of the latest fascinations. Part of its allure is its mysteriousness, as not everything about it has been discovered. And when scientists began to pick up numerous FRB signals within a short period of time, the excitement couldn't be contained, and the signals won't stop. Space is full of deep mysteries that may take us forever to unravel, and FRB is one of them. And receiving these FRB signals is suggesting that somebody wants our attention, should we answer the call. But what exactly is FRB? FRBs are intense bursts of radio emission that last milliseconds. They exhibit the characteristic dispersion sweep of radio pulsars. The first FRB was discovered and documented in 2007 by Lorimer and Co. However, pursuing archived data, scientists realized that FRB were actually observed about 6 years earlier in a pulsar survey of the Magellanic Clouds. Because one of the people that discovered it was named Lorimer, FRB is also known as the Lorimer burst. When a telescope captures an FRB, one of the most important features researchers look at is something called dispersion. Dispersion is basically a measure of how stretched out an FRB is when it reaches Earth. The plasma that is found between stars and galaxies causes all light, radio waves included, to slow down. However, lower frequencies feel this effect more strongly and slow down more than higher frequencies. FRBs contain a series of frequencies. The higher frequency light in the burst gets to the Earth before the lower frequencies causing the dispersion. Researchers try to use this dispersion to estimate how far from Earth an FRB originated. The principle is that the more stretched out an FRB is, the more plasma the signal must have passed through and the farther away the source must be. So let's quickly tell you what the first FRB looked like. It was like giant pulses from radio pulsars like the Crab with extreme intensity and observed across a 288 MHz radio band. It was traced to near the location of the small Magellanic Cloud. Meanwhile, the scientists could not measure the flux exactly because of the limited dynamic range of the instrumentation, but the first FRB has been estimated to be able to occur in several 100 bursts every day with a small probability of detection. Now, for many years after the first FRB, it was thought to be unique, and one of the convincing pieces of evidence of its existence was that it occurred in 3 of the 13 beams of the park's multi-beam receiver. Some years later, a Swinburne student named Sarah Burke-Spoleyor published some disturbing findings that she got from reanalyzing 2 other pulsar surveys. She was hunting for other bursts and ended up with the discovery that at almost the exact dispersion of the Lorimer burst, there were other swept sources of radio emission, but that they occurred in all beams. At this point, interest in FRBs had started to wane. However, fast forward to 2013, and a dramatic thing happened in the subfield of FRBs. Thornton & Co. detected another 4 Lorimer bursts. This was when they were officially named fast radio bursts, or FRBs. The FRBs discovered by Thornton & Co. had dispersion measures that were significantly higher than the original Lorimer burst. These 4 bursts were found as part of the high time resolution universe surveys conducted at the park's 64-meter radio telescope. The brightest of the bunch displayed a classic dispersion sweep and showed scatter broadening with power law dependencies exactly like we'd expect from true extraterrestrial sources of radio emission. Meanwhile, the first FRB discovered in another observatory was announced in 2014. It was recorded at Arecibo and was traced to the direction of the galactic anti-center. However, they have remained controversial in their source, and that is exactly what scientists are trying to figure out because it's just baffling. The mysteries deepened when scientists analyzed a set of data obtained in 2019. The analysis took place in 2021 and revealed 1,652 flares were produced in a period of just 47 days. The flares were from the FRB 121102 source. It set the record for the number of flares discovered from any FRB, but it also opened up a new perspective to researchers about FRBs, investigating or searching for periodicity or regular time spans between similar bursts. However, the scientists were disappointed because they couldn't find any sign of periodicity. They complained that the lack of periodicity posed a problem. It made it challenging to pinpoint the source, to nail it down to a spinning compact object, for example, from a highly magnetic dead star or magnetar. But it was enough for the scientists to suggest that these FRBs could be produced from more than one mechanism. They also had to accept it might be a long while before we understand FRBs or even decode them if they represent secret messages. The lack of periodicity aside, most FRB sources flare once, and that is all. Scientists don't hear from them again. This has been another challenge when predicting or trying to trace them. However, a handful of the FRBs have been giving off signals repeatedly. One of the most prolific is FRB 121102. Its repetition has allowed scientists to trace it to a dwarf galaxy 3 billion light-years away. But of course, it's a real weirdo. It is extremely active and follows a pattern. It has a 90-day period of activity followed by 67 days of silence. The level of activity of FRB 121102 has given astronomers the chance to catch it when emitting. One of the instruments that have helped detect this particular FRB is the 500-meter Aperture Spherical Radio Telescope, or FAST. The telescope started picking up FRBs even during its commissioning stage. In just 2 months, FAST gathered the data mentioned earlier in a 47-day period over a cumulative total of 59.5 hours. The peak rate was 122 bursts over the course of 1 hour, or the highest level of activity we've ever seen in a fast radio burst source. This massive haul of detections allowed for statistical analysis of the source's activity. The researchers categorized the bursts into 2 different kinds, with higher energy and lower energy bursts displaying distinctly different properties. The weaker ones turned out to be more random in nature. However, the lack of periodicity from most other FRBs has not stopped scientists from trying to trace them. Those they could trace were found to originate from galaxies that are millions and even billions of light-years away. But even though they are so far away, they produce bursts so powerful that within a few milliseconds, they can discharge the energy equivalent to hundreds of millions of our Sun. More recently, scientists discovered another FRB which was named FRB 190520 using the same FAST telescope in China. One of the interesting features of this FRB is that it's one of the few repeating bursts. It also repeats itself more frequently than the others. It produces 75 bursts in just 6 months. The team then used the Very Large Array radio telescope located in New Mexico to study the FRB more. They were able to successfully pinpoint the location of its source. It came from a dwarf galaxy roughly 3 billion light-years from Earth. One of the things the team discovered was that there was a persistent, though much fainter, radio signal being emitted by something from the same place that FRB 190520 came from. Of the more than 800 FRBs that have been discovered to date, only one other has a similar persistent radio signal. Since the team could determine that the FRB came from a dwarf galaxy, they could determine just how far away that galaxy is from Earth. But that was where the results stopped making sense. To their surprise, their distance estimate based on the dispersion of the FRB was 30 billion light-years from Earth, which is actually about 10 times larger than the actual 3 billion light-years to the galaxy. That is both usual and unusual. Out of the 800 FRB sources, only 19 have been traced to their origins. This means the distance from Earth can be ascertained for those 19, but for the remaining FRBs, astronomers have to rely on dispersion alone to estimate their distance from Earth. For the other 19 FRBs with known locations, the distance is estimated from the dispersion, very similar to the real distances to their source galaxies. But this new FRB is different because the estimates made by the dispersion method were incorrect and threw many assumptions out the window. And the discovery of FRB 190520 raised even more questions which have still not been answered. For instance, are persistent radio signals becoming more common? What conditions produce them? Is the same phenomenon that produces FRBs responsible for emitting the persistent radio signal? Another thing that baffled scientists about FRB 190520 is that the dispersion is greater than it should be. What could have caused it? Is the cause something near the FRB? Is the cause associated with the FRB itself? The team that discovered FRB 190520 has committed to continue studying it using a host of different telescopes around the world. Perhaps the discovery of more FRBs in the future will allow scientists to understand them very well. Strange objects around the Milky Way. Scientists have also discovered that something is going on in the supermassive black hole at the center of our galaxy known as Sagittarius A star. And on top of that, astronomers have spotted a weird new class of objects not far from the black hole. Normally, these objects appear compact, but they stretch out when they are near the black hole during their orbits, which can last from 100 to 1,000 years. In 2005, scientists spotted an object at the center of our galaxy which they dubbed G1. Later, they found a second object in 2012, which they named G2. By 2014, G2 had been spotted close to the black hole. It is believed that G2 was initially two stars that orbited the black hole together but merged into a single giant star and became obscured by a thick gas and dust cloud. Recently, scientists found 4 more objects, which they named G3, G4, G5, and G6. They orbit differently from G1 and G2, which are similar to one another. The researchers believe that all 6 objects are the result of binary stars or pairs of stars that orbit one another that were forced together due to the strong gravity of Sagittarius A star. And they believe that the merging of stars may be happening in the universe more often than they have believed. It is believed that the black hole may be causing the stars to merge, and that most stars that are observed now may be the end product of mergers that are now calm. The interaction between galaxies and black holes is evolving and has been confusing scientists, which is why they are putting in more work to learn about this interaction. As much as these mysterious objects found near the Milky Way are similar, G2 is different because it didn't undergo much stretching like the others. Scientists believe that something must be keeping G2 compact and also making it survive its encounter with the black hole. Looks like there's a stellar object in the G2. Also, the fact that these G objects are found near Sagittarius A star, which likely swallowed up the gas it ripped off the stars, means they could actually be feeding the constantly voracious black hole. It is also proof that there is a complete disorder not only in the Milky Way, but also in other galaxies. So far, we've only been able to map out exoplanets possibly capable of supporting life, none of which has yielded any form of intelligent life. But that all changed when scientists intercepted a signal from space originating from the region of Proxima Centauri, the closest star to our solar system. The discovery of this signal changed the possibility of extraterrestrial life beyond Earth. But where and how did this radio signal come from, and what have scientists concluded to be the possible source? Proxima Centauri is by far the most interesting star system studied by scientists here on Earth. Being the closest stellar neighbor to our Sun, located just 4.2 light-years away, this star is much smaller in size and mass and sits in the southern constellation of Centaurus. Discovered way back in 1915 by Robert Inner, Proxima Centauri isn't visible to the naked eye, with a quiescent magnitude of just 11.1 and can only be observed via telescope. Much like our solar system, Proxima Centauri has stellar bodies which have been identified as exoplanets orbiting it. With a mass of roughly 12.5% that of our Sun's, Proxima Centauri is a dwarf star with a much larger average density, about 33 times that of the Sun. This means the star is much heavier and exerts a stronger gravitational pull on the stellar bodies that orbit around it. And although Proxima Centauri has a very low luminosity, it is categorized as a flare star which randomly and quite violently releases solar flares packed with high levels of radiation. These flares impact the 2 known exoplanets that orbit the dwarf star, Proxima Centauri b and Proxima Centauri d. There is another candidate exoplanet, Proxima Centauri c, orbiting around 220 million kilometers from the dwarf star, completing one orbit once every 5.2 years. But due to its apparent distance from the star, the existence of Proxima Centauri d is still heavily debated by astronomers around the world. The existence of the other 2 planets has been confirmed and is currently being studied by astronomers and scientists. Proxima Centauri b orbits the dwarf star at a distance of 7.5 million kilometers, completing a full rotation in just 11 Earth days. It is fairly similar to Earth with a mass of just 1.17 times that of Earth and rotates within the habitable zone of Proxima Centauri. At this range, it is possible for atmospheric formation, and temperatures are just right for the formation of liquid water on the surface of the exoplanet. But this has been highly debated by scientists, as Proxima Centauri is a flare star and randomly releases bouts of electromagnetic radiation and solar flares that would make habitability on Proxima Centauri b highly unlikely. Proxima Centauri b receives about 10 and up to 50 times as much radiation on its surface as we do here on Earth. High levels of radiation on Proxima Centauri b could lead to increased levels of oxygen and carbon monoxide, which may build up in whatever atmosphere the planet has. But these high oxygen levels may lead to the evolution of complex chemicals and organisms which could possibly account for organic life on the planet. This idea has been floated around by scientists who believe Proxima Centauri b might have an entire atmosphere filled with organisms, which could possibly be the reason and source behind the signal which recently emanated from the region. The possibility of water on the exoplanet could also lead to chemical reactions which could be conducive to the development of life, and as such may cradle some form of extraterrestrial species, all of which still remain theories at this stage. However, the planet still possesses certain properties that could make it a possible Earth-like planet, and is the only planet within proximity to Earth outside our solar system that could be studied for interplanetary travel. Although it will take any current rovers or satellites we have thousands of years to reach the planet, it still holds promise for life outside of our solar system. But although space vessels may not reach Proxima Centauri b anytime soon, scientists studying the region with telescopes here on Earth recently discovered a signal that could only be described to have emanated from intelligent life. In April of 2019, a radio signal was detected and believed to have originated from the region of Proxima Centauri. The signal, which has since been named Breakthrough Listen Candidate 1 or BLC-1, was detected as a result of the Breakthrough Listen project, which is an initiative set up to search for intelligent extraterrestrial communication throughout the universe. The project has received over $100 million in funding and has dedicated thousands of hours of telescope watch time in state-of-the-art facilities across the planet. Beginning in January 2016, the program still remains the most comprehensive search for extraterrestrial communication outside of our solar system. The signal or techno-signature was picked up by the CSIRO Parkes Radio Telescope in New South Wales, Australia. At the time of the discovery, the telescope was observing the region of the closest star to our Sun, Proxima Centauri, which it had done hundreds of times before. Over time, the telescope picked up vast amounts of data, and scientists didn't pick up the signal right away. At the end of each observation cycle, they had to filter through hundreds of thousands, sometimes millions of signals to single out any unique techno-signals which might originate from space. And to give you a sense of what they are looking for, the signals must have two distinct properties. The first was that it must be confined to a very narrow broad band of frequencies, much similar to radio broadcast on Earth. This is unique because no natural process is able to produce this kind of signal, and it will definitely raise red flags if it were to originate from space. The second property is that the frequency of the signal must drift in a way that is similar to the motion of exoplanets relative to Earth. During this particular observation cycle, the telescope in Australia picked up over 4 million distinct signals, and the team had to get to work filtering out unimportant signals and leaving out the rest. The team was able to filter out much of the background signals that originated from Earth and were left with over 5,000 distinct signals. The team then had to further cross-check these signals with radio transmitters currently on Earth and were finally left with a single, unexplained signal. The team of scientists described this signal as a unique techno-signature with a narrow broadband that appeared over a 30-hour observation period and only when the telescope was pointed towards Proxima Centauri. The discovery of BLC-1 indicated that it possibly originated from Proxima Centauri and had a distinct feature to the WOW signal discovered back in 1977. The WOW signal was a strong narrowband radio signal discovered by Ohio State's Big Ear Radio Telescope, which was the premier tool used in the search for extraterrestrial intelligence. The WOW signal appeared to have originated from the constellation Sagittarius and was the first sign of extraterrestrial communications outside our solar system. The signal lasted for about a 72-second window and has since not been detected by any other telescope anywhere else in the world. There have been several hypotheses to the origins of the WOW signal, including human-made sources, none of which have adequately explained the signal's origins. It currently remains the strongest possible evidence for a radio-transmitting extraterrestrial civilization outside the solar system. But although BLC-1 had similar properties to the WOW signal, scientists at the Parkes telescope needed to ensure they had eliminated every other possibility that could explain the origins of the signal. This was paramount because attributing a radio signal to extraterrestrial civilizations was to be made as a last resort when no other possible hypothesis could account for the signal's origins without a doubt. To this end, a remarkable level of investigation was put into eliminating any conventional explanations for the signal's origins. First, the team began observing Proxima Centauri almost 2 years after the initial signal was detected in an attempt to replicate the initial observation conditions which led to the discovery of BLC-1. The team has been unable to locate any evidence of a signal similar to BLC-1 in the Proxima Centauri region. The team then went on to investigate the possibility of a moving transmitter which could explain the source of the signal. This included moving objects such as trains, planes, helicopters, balloons, and any other electronic device capable of transmitting signals long range. However plausible this angle of investigation was, a moving transmitting object could not sufficiently explain the fact that BLC-1 appeared constantly over several hours. The team came to the conclusion that a moving transmitter could not possibly explain the trajectory which produced the drift of BLC-1 for such a long period of time. In a statement to the press, the team stated that it is extremely difficult to construct a continual motion path that could persist as exhibited by the measured signal, even by varying the speed along the route. The team also came to a similar conclusion when investigating satellites as possible explanations for the origins of BLC-1. This is because satellites in low Earth orbit move too quickly to produce signal drifts for such long periods, and geostationary satellites do not drift at all. It was concluded that no satellite in orbit could have possibly produced BLC-1. Then the team moved on to investigate deep space probes such as Voyager 1 and 2 as possible origins of the signal, with the probes being the only man-made signal-transmitting objects in deep space. But the team was also able to rule out these probes as none of them were in line with the telescope or remotely within any region close to Proxima Centauri. The team finally decided to study the signal itself, which they then noticed had an apparent shift consistent with the Doppler effect. This in turn suggested that the frequency itself was inconsistent with what could have been caused by movement on Proxima b or any planets orbiting Proxima Centauri. The signal itself had a frequency of 982.002 MHz and having a Doppler shift that increased in frequency rather than decrease. This prompted the team to look at drifting signals similar to BLC-1 in the previous data, which had been discarded earlier on in investigations. Surprisingly, they found 5 similar signals to BLC-1, and after looking further, found 27 other mirror signals of BLC-1, and it was at this point the signal's origins became clear. The signal frequencies were multiples produced by interactions of common clocks and other digital electronic devices. Apparently, the Parkes telescope was picking up on its own radio frequency interference, although an albeit rare and minute form of it. The complexities of BLC-1 just go to show the intricacies involved with searching for extraterrestrial communication in the universe and have served as a checklist for future signal discoveries. Do you think we'll ever discover any extraterrestrial communications in our lifetime? Let us know